particle filtering was this way of doing reasoning under uncertainty through time, that here is the transition function and here's our sensor model. Hidden Markov models are exactly the same. So if you're happy with this, you'll be happy with the next slide. This is a good time to show this slide. Show this one here. So for a particle filter, the next state, you were in a particular state, and you went to the next state, and you also had some evidence, some observations. So at every state, you got a little bit of, I don't know if you want to call it O or E, or I don't know. Different people use different letters. I don't care. This is the graphical model of a particle filter, of a stochastic system with partial observability. With something like particle filtering, you don't get to view the actual state of the robot. All you get to view is these observations, and you're trying to find the underlying state that's most likely given the evidence. This comes up all over the place. People have worked on this since the 40s. Like you get this sighting in by some drunk sailor saying that he saw a periscope, in Chesapeake Bay, and then everyone's wondering, oh my God, what's the probability that the Germans are, going to lay mines in the harbor right next to our nation's capital? So trying to figure out what's going on based on noisy measurements is very, very important. Now, so this is the model, and it's just what we just said. The probability of being in state J at time t, people usually use x for the state of the system. Probably the state at time t is J, we're in state J, is equal to the sum over all the states we could have been in at the last time step times the probability that if we were at I the last time step that we would have transitioned to J at the current time step. This is the transition model of the system. And here is the sensor model. So the probability that we would get an observation k at time t depends on, well, we go for every possible state we could be in at time t. There's some probability that given we're in that state, we would emit that, we would receive that sensor reading. Does this make some sense? Yeah, so this is very, we've been dealing with this kind of stuff ever since MDPs. This is the new part here. Now, we don't want to do POMDPs because they're super complicated, so we're doing something a little bit simpler. We're not choosing actions. We're just observing a system. So this is just the same thing, but with fewer characters. So it looks simpler, but it's really exactly the same. The probability of being in a particular state at time t is the sum over all the previous states of the probability we're in that previous state times the probability we would transition from that state to this state. And then the probability of getting some observation is the sum over all the states we could be in of the probability of being in that state and the probability of getting that observation from that state. Now, so that's a hidden Markov model. Why is it Markov? Yes, sir. Absolutely. Why is it hidden? It's a hidden Markov model, HMM. It's a model because it's got variables instead of like submarines. And it's Markov because it's the probability of a state transition only depends on where you previously were. It doesn't depend on, like, give me your entire life's history and then I'll tell you the distribution over next states. We're summarizing everything in a single, in the state. And what's hidden about it? Yeah, exactly. We don't get to see this. We just get evidence. HMMs are what's used in speech recognition. You have no idea what the person said. You hear these sounds, and thank God the sounds are related to what the person was saying. But if somebody says it can be very hard to recognize speech, that sounds an awful lot like it's very hard to wreck a nice beach. So there's a lot of ambiguity. And you can't go from the sound to like what's the most probable word with that sound. That totally does not work. People tried that in the 70s and it was a massive failure. HMMs came along in the 80s and whoa, all of a sudden speech recognition actually worked. And it takes into account the transition model between the states. Namely, certain sequences of words are much more likely. So I had a friend that worked at Dragon Dictate, which was the leading speech company for a while. And he worked on language modeling. Like, it wasn't about the phonemes, like people had done that in the 70s. It's all about this, all about the state model. What's the probability of a given sequence of words? And if you can say that this sequence of words is more likely than that sequence of words, then given a lot of ambiguity in the sensor readings, you can use this model to help you disambiguate and figure out what was more likely. Let's see, there might be a better example.
So would those speech recognition things do poorly if you just started spitting out random words?
Yes. Yes, very poorly. Especially if you're on a phone. The signal on a phone is terrible. So anyway, so that's a hidden Markov model. Now, so the classical problem for a hidden Markov model is, given a sequence of observations, what did the system actually do? What was the most probable state sequence? Oh, yeah. We don't want to do this today. Let's do this next time. Just so you've seen it twice, though. So the problem is, you're given the model, the transition model between states. Here I use the letter S and O instead of E. Don't kill me, sorry. S, the transition model, sensing model, sequence of observations. Find the most probable series of states that I could have gone through. And the thing I just want to point out with this is, A, it's just dynamic programming. So if you took algorithms, you're like totally at home here. B, it takes into account both the transition model and the sensing model, just like you'd think it should. So you're finding, what it finds is the most likely sequence of states, given both the transition probabilities and the probabilities of getting those observations in those states. And so we're filling out a giant dynamic programming table here. Well, it's not giant even. It's just like a rectangle, S by T. So you start off in some start state, which is like the person hasn't even spoken yet. And then you end at like the end of the utterance. And then you try and figure out what the most probable words are.